Our next presenter is a staff engineering manager at Github. He managed the semantic code team, which applies academic programming language theory to analyze all the code hosted on GitHub. Our presenter's name is Douglas Creager, and his presentation is entitled A Whirlwind Tour of My Favorite Programming Languages and Three Others. It's all yours, Douglas.
Great, thanks very much for the intro, John. As John mentioned, my name is Doug Creager. I'll be presenting to you virtually from my home here just outside of Boston. And I manage the semantic code team at GitHub. We're part of the larger code productivity space at GitHub. And we focus on developing developer productivity features like code navigation. Teams next to us work on code search, vulnerability exposure analysis, those kinds of things. And what's sort of unifying across all of those features, all of those product features, is that they all work based on the idea that we can analyze the code that's uploaded to GitHub. And importantly, those are features that we want to be available for everyone that uses GitHub, which means that we're exposed to all of the programming languages that are hosted on GitHub, which, if you think about it, is basically the same thing as all of the programming languages in the world. So we have an interesting, very wide perspective on programming languages, which I hope to share with you today. So we often like to compare programming languages with spoken languages. And so I want to start with a pretty famous myth from the Old Testament. So what you see here is a painting from the late 1300s depicting the Tower of Babel. If you're not familiar with this myth, the Tower of Babel is meant to explain why people speak different languages. And the story goes that after the great flood of Noah, the human world was united as a single people who all spoke the same language. And they were so proud of themselves and their accomplishments that they decided to build a tower tall enough to reach the heavens. And as often the case in the Old Testament, this is a story of God punishing humanity for its hubris. And in this case, he sundered the people, spreading them to the corners of the earth and causing them to start speaking many mutually unintelligible languages. So how does this relate to the history of computing and of programming languages? It's admittedly not a perfect analogy. I can't claim that there was any single programming language that the world's programmers all used in the prehistory of computing. In fact, starting in the 40s and the 50s, there were several groups that were simultaneously trying to build human-readable programming languages on top of machine code and assembly. But we can say that there are a small handful of languages like Fortran and COBOL that we consider to share the crown of being first. And again, not exhaustive. There are others. These are just two that I've called out. Now, how else is this analogy strained? Well, programmers are certainly guilty of hubris, but I'm not going to try to claim that divine retribution sundered the world of programmers in the 50s and 60s. But nevertheless, the end result is the same. Today, there's a plethora of programming languages. This wall of logos that you see here might seem like a lot, but it's actually only a small sample of the languages that exist today. So as an example, GitHub maintains an open source package called Linguist, which is a crowdsourced list of all of the languages that we're aware of. And it currently contains more than 500 entries. Now, as an aside, just throwing these logos up here has probably nerd sniped several of you. So let's go ahead and play a game of Pyramid. There's 35 logos on the screen. And Dick Clark wants to know how many of them you can recognize. Just a competition with yourself. It's okay if there's a lot that you aren't familiar with. But it's a fun little game if you want to play along at home. So now for me, the most interesting part of our Tower of Babel analogy is the mutual unintelligibility part. So like spoken languages, there are families of programming languages where within a family, if you're familiar with one of the languages in that family are probably similar enough that you're likely to understand at least the basics of another. But if you leave that family, if you look at another family of languages, the very concepts of programming might be so different that it can be almost impossible to understand how those languages could possibly work. And I'd claim that most of us these days are really only familiar with one programming language and its ecosystem. We're aware that other programming languages exist, but we don't really take the time to explore those other languages to learn where the similarities and differences are. And to be clear, that's perfectly okay. We all have a limited number of hours in the day. Time is the most finite resource. Learning other languages might genuinely not be the best use of your time. But there is a multitude of languages out there, and I believe it's one that's worth exploring. So for the next 20 minutes or so, we're going to explore that multitude together. My hope is that regardless of which language you're most fluent in, you'll see something new that makes you think about programming differently. I firmly believe that knowing about other programming styles and paradigms can make you a more effective developer. And also to clarify, I'm going to be relentlessly positive here. This is definitely not a sermon about one true programming style that everyone should switch over to. I'm not going to make any value judgments regarding static or dynamic typing, for instance. For those of you following along in the chat room or at home afterwards, I would encourage you to please stay positive as well. Okay, so let's jump in. To get our feet wet, we're going to start by looking at some very high-level patterns that show up time and again. Our first pattern is repetition. What facilities do our programming languages give us for performing the same work over and over? We'll use a pretty simple example to start with, computing the Fibonacci numbers. If you're not familiar with this sequence, the first Fibonacci numbers are 0 and 1, and each subsequent number is the sum of the previous two. And so we're going to start by looking at an implementation of Fibonacci in Go, which uses a for loop for that repetition part. We need to keep track of the previous two values. Here I'm going to call them A and B. And then we just loop through the numbers that you've requested, calculating the next value and sliding it into our window of previous values. Once our loop finishes, we know that A will contain the Fibonacci number that was requested. Now, Go is an example of an imperative programming language where the bulk of your program consists of a sequence of statements that are executed in order, one after the other. The for loop and its cousin, the while loop, are ubiquitous in imperative languages. That's going to be the primary way that you drive a repetitive process. Now, most popular languages these days are imperative. And in fact, we can look at this same Fibonacci example in Perl, or in Python, or in C, or in C++, or in Rust. And in all of these cases, the implementation looks more or less identical, just with slight differences in syntax. But loops aren't the only way we can repeat ourselves. Another pattern available to us is recursion, where you define a function that calls itself. And by calling itself, you sort of perform the body of the function over and over again, and you get the repetitive behavior. Here we can see a recursive definition of Fibonacci in Haskell, a functional programming language. A defining characteristic of functional languages is that modifying variables is prohibited, or at least it's greatly frowned upon. Now, one nice feature of this functional implementation is that it's very similar to the mathematical definition at the bottom of the slide, which we're trying to implement. And so that means that you can, by inspection, more or less, see that the code that you've written is correct, assuming that you've got that nice mathematical definition to compare against. Now, this style, this recursive style, is not limited to functional languages like Haskell. We can implement it in imperative languages too. And so here's what it looks like in C. Again, it's the same pattern. It's a function that calls itself, and that's how we get the repetitive behavior. Now, one problem with this implementation, both the Haskell one and the C one, is that it's slow. It might not be obvious, but if we look at the definition of this function and analyze it for a bit, we can see that we're doing an exponential amount of work. Because we end up calculating each previous Fibonacci number multiple times. And that just builds up more and more as you progress down the list of Fibonacci numbers that you're having to calculate. And I want to point out, this is not a problem with recursion in general. This is just a problem with this particular recursive implementation. So we might try to fix it while being recursive by maintaining the previous two values in variables like we did in the imperative loop implementation. Now, again, in a functional programming language like Haskell, you're not allowed to modify variables. So the way we do this is we actually use function parameters for those bits of state that we need to modify, update during each iteration. And that way, when we make our recursive call, we can provide new values for A and B, just like in the loop-based version, we just overwrote the existing variables each time we would progress through the loop. But importantly, this ends up having the same efficient execution behavior as our original imperative version did. And again, like before, this is not a pattern that's limited to functional languages. We can do it in C as well. And you can see that, again, we have A and B as parameters instead of as local variables, but we still update it each time we do a recursive call, which is analogous to how we were updating the variables in each loop iteration in the loop-based version. Okay, so another interesting benefit of that recursive style that we just saw, and of functional programming in general, is that it makes it easier to look for even higher level patterns. So not just, oh, there's lots of problems that we can solve with recursion, but even going deeper and looking at all of those instances of recursive functions. How many times do we recurse? How much work are we allowed to do before the recursive call? How much work after? And in the functional programming world, the answers to these questions lead to a number of different recursion schemes. And now if you look at these names, they can definitely sound strange if you're not used to them, which might emphasize how, to me at least, the mutual unintelligibility part of the Tower of Babel myth is the most striking part of it to me. But these names do have very specific and precise meanings, which is useful if you're using functional programming as a lens to explore deep topics in computer science. Now for today, I'm not going to go into the details. I'm just going to point out that the Fibonacci sequence is an example of what we call a histomorphism. And the histo part has the same root as the word history. And what this signifies is that each of the recursive steps needs access to the full history of previously computed values. And so here's what Fibonacci looks like in Haskell when implemented as a histomorphism. So you'll notice you don't actually see a recursive call here. There's no place where fib calls itself or where our step subfunction calls itself either. The recursion is actually encapsulated into the histo call that we make. What we have to provide is just this step function that is given the list of previously computed values, and it's allowed to analyze that list and compute from that list however it needs to in order to produce the next value. Okay, so we've finished talking about repetition. Let's move on to our next pattern, which is error handling. How do we handle failure that occurs in our programs? And you might be surprised to learn how many different error handling strategies there are out there. So for our running example in this section, we're going to look at some code that can parse a single digit stored as a single ASCII character and extract that into a corresponding integer value. And now this is a process that can fail because not every ASCII character is a digit. And we need to think about how we're going to detect and model that failure. So to start with, we're going to look at exceptions. Many languages use exceptions to handle these kinds of error conditions. Java is probably the most well-known example. And so here is what our parse digit function could look like in Java. You'll see that like we have the first part of our function is verifying whether the character that is passed in is in range. And if so, it's doing some arithmetic to figure out its integer value. But if it's out of range, then we fall through and we throw an exception to signal that error condition. Now, Java is not the only exception-based language. Here's the same example in Python. And here it is in C++. And so a good way to think about this is that an exception is going to abort or interrupt the flow of your program. So the function throws an exception instead of returning a value. And at that point, your program starts unwinding its call stack, like going to the caller of this function and the caller of that function and so on, looking for some code that knows how to handle that exception. So we can expand our C++ example here to show how that exception might be handled in this language via what's called a try-catch block, which you can see in the use file function at the bottom. This kind of statement runs the code that appears in the try clause. And if any part of that code, including any functions that it calls or that it calls, however nested it needs to go, if any of that code throws an exception, the catch clauses have a chance to handle that exception. Now, you should notice here that the exception might not be handled by the immediate caller of the function that threw the exception. So here, parse digit throws the exception. Parse file is what calls parse digit. Use file is what calls parse file and is where the exception is handled. So if you zoom in and look at parse file, it is going to, if you will, silently propagate any exceptions that occurred. And there's no mention of exceptions in that file, but it still participates in this exception mechanism. And that's one of the defining characteristics of an exception-based language. It's your callers that get to decide where and how to handle those error conditions. And they might silently propagate through functions that don't mention exceptions at all. And some people like that because it means that many of your functions can focus on the happy path and not have to really worry about explicitly handling error conditions. But other people don't like that pattern because they feel that the implicit control flow is harder to reason about. So now let's look at the opposite end of the spectrum. This is what our parse digit function might look like in C, where error handling is very, very explicit. In C, there is no single error handling strategy that's used everywhere consistently. But a common pattern is that you would use a special sentinel value to indicate errors. So here, our parse digit function only needs the values 0 through 9 for successful results, which means that we can use any other integer value that we want to indicate an error. And a common convention in C code is that you would use -1 for error codes like that. But otherwise, the structure is not really all that different than what we saw in the exception-based version. We still need to detect the error condition. Here, we just use a return statement instead of a throw statement to signal that error to our caller. But the changes are more obvious where we handle the errors. So in particular here, you'll see that the parse file function does have to know about and participate in error handling. It has to explicitly interrogate the return value, and if it is an error value, return an error ourselves from our function. So it's explicitly propagating that up the call chain, whereas with exceptions, all of that happens silently and implicitly. So we can look out at some other languages that also use this error handling mechanism. In Go, for instance, the structure is very similar, but here we get to take advantage of the fact that Go functions can return multiple values. So you can see that in parse digit, where it returns both an int and an error. That means that we don't have to reserve a sentinel value to indicate errors, which is especially useful if we need every possible value as a potential return value in the successful case. And it also means that we can encode errors using their own specific type, which means that if we want to, we can put more detailed information into that error value about what error occurred and additional properties of that failure, if that's helpful. So in this case, again, parse digit returns both a normal value and an error, and the caller knows that only one or the other should actually be used, depending on whether it's a successful parse or an erroneous one. Rust is going to look similar. We continue to use regular values to encode our errors, but here we get to more directly express that idea that parse digit returns either a successful result or an error. That's encoded into this result type that Rust provides in its standard library. In Go, our function returned both values, and we relied on the caller knowing that there was a convention that needed to be followed. It needed to know that the result value wouldn't contain any useful data if the function returned an error. In Rust, that is encoded in, like I said, into this result type where it's not possible for a result to contain both the successful value and the erroneous value. Now, Rust also requires intermediate functions to explicitly propagate errors, just like we saw in C and in Go. Here, though, it adds this nice question mark operator, which helps remove some of the boilerplate involved. So in this case, parsefile is still doing manual explicit propagation of errors. It just takes less space, less characters in our function, in the actual text of our source code to accomplish that. Now, lastly, error handling is not specific to imperative languages. Errors can occur when using a functional language too. And so here's what our example looks like in Haskell. It's very similar to Rust, although here we actually don't get to see it because of type inference, but there is an equivalent to Rust's result type here that parse digit returns. It's just that in Haskell, that's actually called either, where, like we were talking before, how it returns either a successful result or a failure result. In Haskell, they actually call it either as a result. The other interesting thing to point out here is that parsefile is still doing the explicit propagation of errors. It's using this do notation to do it with even less ceremony, even less boilerplate than we saw in the Rust version. So we don't even have to see the single character question mark operator. Now, this works because Haskell's either type is what's called a monad. That's another esoteric functional programming term, just like our histomorphism and other recursion schemes that we saw before. And we definitely do not have time to get into what a monad is or is not. If you want to go down that rabbit hole, definitely check out some interesting monad tutorials online, or we can handle that in Q&A afterwards if people want to. Okay, so moving on to the next section, the next set of examples. We've talked about repetition, we've talked about error handling. Next, we're going to talk about how you clean up after yourself. Now, this is especially important for long-running programs like servers. If you need to allocate or acquire resources as part of handling a request, but you don't release those resources when you're done, you're quickly going to exhaust all of your available capacity, and that's bad. Now, the original resource that programs have had to manage since the dawn of computing is memory. So to start, we're going to look at what's needed in C to allocate and deallocate values from what's called the heap, and where there are no language facilities to help you do so. I mean, there's the malloc and free calls that actually do the allocation and deallocation, but there's no help with the bookkeeping to keep track of whether you've successfully deallocated things when you need to. So here you can see a data type along with helper functions for allocating and deallocating instances of that type, again, that live on the heap. And I want to call out especially that one of the fields, the name field, is itself something that needs to be managed because we make a copy of the name. So the name field is allocated on the heap, the person is allocated on the heap, and so then at destruction time, we have to go through and free both of those in order to correctly and fully clean up after ourselves. And here we can see an example of how you might use these functions to handle instances of this new type. So we create a person, we do some computation with it. Here we're just printing out its contents. And then we're very careful, we free it when we're done with it. And because you're managing resources manually, you'd better make sure you do so. If you forget this person free call here, then you're going to have a memory leak and things will be bad. So I'm not going to lie, this is very cumbersome, like this pattern in C, to have to manually manage your resources like this. But it's interestingly not all bad. I think it has a bad rep, but there is a genuine benefit to this style, which is that you can see precisely in your code where everything is acquired or released. And so in that case, in that way, in some ways, it's actually easier to analyze what your code is doing because it's all visible directly in the text of the program. And that's especially useful for low-level programs or real-time programs where you really want to have an assurance that every instruction that the CPU is performing is due to code that you wrote. Now, I think it is fair to say, though, that most programmers have decided that that benefit is not worth the extra work that's needed to manage resources manually, at least for memory. So if you want to avoid that manual bookkeeping, a nice simple choice would be to use a language that does this bookkeeping for you. So here we can see that same example in Go and in Python, both of which use garbage collectors to manage the memory for you. So you can see that in the function that uses this new data type, we do have to create the instance of the type that we want to work with, but we don't have to do anything explicit to free it. Now, garbage collection is not your only option. There's other ways to do automated memory management. And in C++, smart pointers are the way that you would do so. So here is the C++ version that we saw that's the equivalent of the C version that we saw, where we're managing the memory manually. So you can see that it's not using malloc and free, it's using new and delete, but you can still see that there are explicit operations, instructions in the source text that is performing the allocation and the manual deallocation. But here's the C++ version that uses smart pointers. In C++, they're called unique pointer and shared pointer, which will automatically release the underlying memory when that pointer goes out of scope. So here we have the operations that allocate the memory, but just like in the garbage collected case, we don't have to explicitly put in any instructions to deallocate it. That will happen automatically when the variable is no longer reachable in the current scope. Rust has a similar facility, but its smart pointers are called box and arc instead of unique pointer and shared pointer. Now, sort of moving on from memory, memory is not the only resource that you have to manage. So for example, you might need to open a local file in your program and save some data to it. And your operating system is going to limit the number of files that your program can have open at any time. So what facilities does your language provide to help you remember to close the file when you're done with it? Now, as you might expect in C, the language doesn't really help you. You have to remember to close the file yourself. And now, also interestingly, I want to point out how cleanup and error handling, which we saw in the previous section, interact with each other. So here there are multiple exit points from this function. A couple of those are error cases, and then the last one is the success case. And we have to remember to clean up after ourselves after all of them. So the pattern that we saw in C++ for managing memory works for other resources as well. And the general name of this pattern, it has a cumbersome acronym. It's called RAII, Resource Acquisition is Initialization. And the idea is that there is some object, some value that knows how to clean up itself, and that's encoded in the object's destructor. And C++, the language, guarantees that that destructor will run whenever the value falls out of scope. And so that's what caused unique pointer to free its memory. And that's what's going to cause this OF stream type here to close its file when it goes out of scope. And what's nice is that because RAII is tied to the lifetime of a value, this process is entirely deterministic. You can tell exactly when each resource will be freed. You don't get to see an explicit close operation in your source code, but you can still know precisely where it's going to happen because you can see where the value goes out of scope. Now, this is also nice in that RAII combines nicely with exceptions. So here we have a couple of operations there that could raise an exception if writing to the file fails because the disk is full or you don't have permissions or whatever. And if that happens, again, the file will still be correctly closed because C++, the language, guarantees that those destructors are called, regardless of if you're returning or leaving the scope successfully or because an exception is being unwound. Now, like before, Rust has a similar mechanism. It's also going to use RAII. Here, the file object that you create knows to close itself when it goes out of scope. And just like we saw with C++, this is playing nicely with the error handling mechanism. So here, if either of those question mark operators cause this function to return early, the file will be closed successfully, just like it will in the successful case. So how does this work in a garbage collected language? You might be tempted to use a similar trick and have some kind of garbage collected object manage the resource for you. But unfortunately, it's usually not going to work. Garbage collectors are typically non-deterministic. The guarantee that they give you is that at some point, it will detect that your objects are no longer in use and free them, but there is no guarantee about precisely when that will happen. And that's not good enough for managing resources like open files, where you usually want to ensure that the file is closed as soon as you're done using it. So in Go, the solution is what they refer to as this defer statement. So when you see defer followed by a function call, it doesn't call that function immediately. Instead, what it's doing is it's sort of registering or remembering that function call and guaranteeing that whenever this enclosing function returns, that call will be made before the return statement. But importantly, it applies to every future return statement, which means that it will work for the error returns and for the success returns. And we don't have to go through and remember to manually put those close calls before each and every one of the return statements. Python has a slightly different approach. It uses what's called a with statement. So you provide a context manager, which is a special kind of value that knows how to start and stop itself or open and close itself. And the with statement guarantees that it will be opened before the body of the with statement starts. And it guarantees that after the with statement is done, the object will be closed. And again, regardless of whether that's because it falls through or because it returns or because it throws an exception, however control flow leaves the with statement, Python, the language, guarantees that the context manager will be closed. Now, to wrap up this section, I want to look at another language, Zig, which is an interesting hybrid of all of the styles that we've seen so far. So like C, the Zig ethos is that you want to see something in your program text that represents every instruction the CPU is executing. So there's no hidden behavior like you would see in RAII destructors. It uses a defer statement like Go to ensure that resources are freed. But its error handling is a little bit more like Rust, where fallible functions return either a return value or an error. And it also has Rust's an analog to Rust's question mark operator, though it's spelled out as the word try instead of as a single character. So it's a nice hybrid that shows how all of these decision points that we've been talking about so far are independent of each other, are orthogonal to each other. And there's different languages that might pick and choose different selections from all of the available choices. Okay, lastly, and hopefully briefly, we're running close to time, I want to talk through concurrency. And this is getting into the idea that broadly speaking, our programs are either CPU bound or IO bound. So far, we've seen mostly CPU bound examples, and those programs are limited only by how fast your processor are. It just churns through the instructions sequentially one by one as quickly as it can. And if you have a faster processor, it completes that process more quickly. But with IO bound work, where you're talking to another program over the network, for instance, a defining characteristic of that is that there's a lot of operations that you're performing where you have to wait for something to finish. And you don't really know how much time that will take, and you have no control over that either. And so we need to figure out how to make sure our programs can execute efficiently in the presence of those kinds of blocking operations. So for our running example here, we're going to consider a program that needs to download 3 files from separate servers. And this is what it looks like in Go. And just briefly, for simplicity, we're not actually going to show the implementation of the downloading itself. We're going to assume that there's a function that we can call that does it for us. Now here, the download function is a blocking call. So looking at this code, what you can infer is that this is not going to download the 3 files at the same time. It's going to do so in serial, sequentially. The second download will not start until the first download finishes. And that might not be the best, most efficient use of our network capacity, for instance. We might want to instead say, we should actually try to download all 3 of them at the same time and just let them race with using our network connection to see who can finish the most quickly. So Go provides a facility that lets us do exactly that by creating what's called a new Go routine for each of the downloads. And we just did that by prefixing the call to download with that Go keyword. What that's going to do is it's going to fire off a new background Go routine. This is just another thread of control that can execute concurrently with the current function. And it will go through and do the download, and it can make blocking calls if it needs to. And Go's scheduler, provided by the Go runtime, will do the hard work of making sure that all of the Go routines in your program are sharing the CPU correctly. If one of them needs to block, it'll move it aside and allow another Go routine to sort of step in and start working. So it works really nicely. It was a nice, easy transformation, but we've lost 2 things with this implementation. The first is that we no longer have access to an error value that tells us if the download failed or succeeded. And actually here, we also, the Go routines are running in the background, but we're not doing anything to wait until they finish. So if this is the only thing that your function, that your program calls, we're not going to wait for them to finish, and the program will just immediately finish. Go goes a very long way to try to provide a standard library that helps you solve these kinds of problems. So in particular here, we can use this wait group type that the standard library provides. So inside of each Go routine, we will make sure to register the fact that there's a new task and signal when the task is done. And then after firing off the 3 Go routines, this wait call will then wait for all 3 of them to finish. So this is a common pattern that you might see. And we can sort of collect the errors and return them back if any of them do cause errors. So now we can look at this in another language. Here is a Python version, which looks superficially like it's doing the same thing. We have the join call to make sure we wait till they're done. It's firing off a background, new control flow thread in order to actually do the downloads. The important difference here, though, is that it's spawning OS threads instead of Go routines. The programming model is very similar, right? It's just a new sequential flow of control that gets to do some work. It's relying on the operating system to schedule the threads instead of Go's runtime, though. So this is useful in some ways and not useful in other ways. So in particular, I think a good rule of thumb is that OS threads are heavy because they have a footprint down in your operating system kernel, which means that you should try to avoid creating lots of them, where lots is on the order of like tens or hundreds of thousands. Whereas green threads, like a Go routine, are just regular data structures inside your program, and it's usually not a problem to create even millions of them, if that's what you need to do. Now, on the other hand, a green thread scheduler is its own API, which your code needs to know how to interact with. In the case of Go, this is handled for you by the language and the standard library, but it means, for instance, that it's hard to call code written in another language from your Go code, because that foreign code doesn't know how to interact with the scheduler. And so it doesn't participate in that nice migration of Go routines and detection of blocking calls like Go code does natively. Whereas OS threads, on the other hand, are managed by the kernel, and so they can contain any code written in any language that the machine knows how to execute. But it's also important to call out that that synchronous model with Go routines and OS threads is not the only model available. Another equally popular model is asynchronous or event-driven I/O. And so here we can see in JavaScript, using the async facilities of the language, what it would look like. Again, here we're actually doing the downloads sequentially, which we had said is not what we want. But this shows how you sort of have each blocking call register handlers for events that fire when the blocking call is done. And that's how you chain together the logic that needs to happen in between each of those blocking steps. If we want to make everything happen concurrently, just like we saw in Go, there are language standard library facilities that let us do that more easily. So this promise.all is just creating something that will try to run all of its inputs concurrently at the same time and not return until all of them have finished. Now, looking back at the original JavaScript, though, we can sort of see that this registering of event handlers is already an example of what people refer to as callback hell, where we end up adding more and more additional handler code, and our code starts to sort of drift or creep over to the right as we have to indent. And so languages have tried to solve this with some new syntax. So here we can see what's called async await. These two examples are exactly the same. It's just using new syntax to avoid that sort of nested callback hell example. And what this means is that this is just a function that is going to return one of those futures, one of those promises that will be executing in the background. Inside of an async function, you have to use this await keyword to be able to make calls to other async functions. And here's what it looks like with our promise.all using async await instead. So just like we saw before with exceptions, there's sort of pros and cons to this approach. Some people like this syntax because it makes it obvious in the code which steps could possibly block. Other people dislike the syntax because of what they call the function coloring problem, which means that you can only easily call an async function from some other async function. And so asyncness, if you will, can become viral, requiring you to mark functions as async, even though they're not really doing any blocking work themselves. And then very lastly, this asynchronous pattern is not limited to JavaScript. It's also used in Python and in Rust. So it's, like I said, it's a fairly common pattern that you might see. Okay, so we've come to the end of the journey. We still have a multitude of programming languages, and we always will. But hopefully I've been able to add a bit of order to that multitude for you today. If you've encountered a new style of programming that used to be completely alien to you, please consider if there's any parts of it that you can bring back to your native language and ecosystem. And even if there aren't, you can at least be thankful that you now have a better, more mindful appreciation for the ways that things are done in your language. And if you do find yourself with some spare time for personal learning and experimentation, please consider implementing a toy project in some language that's completely outside your comfort zone. I think it'll be worth the effort. And with that, thank you for your time. John, I think you're muted, sorry.
Yeah, thank you, Doug. That was really interesting. I'd have to say all the languages are alien to me, but it was very interesting. I'm glad you enlightened me on this, and I hope a lot of the listeners learned something from this also. I'm sure they did. We do have one question from you from a person named Anonymous, and his question is, according to the title, what are your favorite languages and why?
That's a good question. Thank you. So I will say that I have a soft spot for C. I grew up as a C programmer, and I want to very carefully clarify that I'm answering the question of what's my favorite, which is not the same question as what would you recommend for new programs to be written in. I know there's quite a lot of commentary out there these days that say, for instance, that anything that you could write in C these days, you should probably write in Rust, for instance. And so I'm not trying to make the claim that I am suggesting that people start new projects in C. I'm just claiming that I enjoy it. When I myself write C, I do find it enjoyable.
Okay, very good.
Yeah.
Very good. Go ahead.
Oh, I was going to say, there's others. I do like Rust as well. I like Haskell, if I'm being honest, not to program in, but to see others program in, because I always learn quite a bit when I see a good Haskell program. I'm just not confident that I myself could write a good Haskell program. So I think that's maybe where I would start with my list.
Okay, that's great, because Anonymous has a comment, and after his question, and his comment is, C would rather return 1 on success, 0 on error, and have a by reference value to put the result with a little kind of frowny face.
That is often a pattern you have to follow, especially when the actual return value from the function, if you need the entire space of values and you don't have a sentinel that you can use to signal error, what that person has described is exactly what you would have to do instead. That's right.
And then finally, Anonymous likes you, so he's got one more question. I agree that knowing multiple languages is beneficial. How transferable are skills you learn in one language to another, in your opinion?
That's also a great question. I think that's kind of why I was trying to choose the sort of section headings that I had today. I was trying to identify some of the kinds of things that I think are more directly transferable. So if you have become used to writing an exception style for error handling in Java, then moving over to Python, at least that aspect of the language should be familiar to you, because it will also use exceptions to signal errors, and they'll be handled in very much the same way. So I think, it depends on the language you're moving from and the language that you're moving to. But I think what I was trying to highlight here is that looking down one level from the language, you can start to identify common patterns that appear, which do happen in multiple languages. And so that's, I think, the way that it does become a little bit more transferable, right? If you're doing imperative programming with exceptions, there's a couple of choices that I think large parts of the day-to-day of doing the programming will be transferable and reusable.
Great, super. That's all the questions that came over on Slido. I don't know if you're going to be around that people can ask you questions directly for a while. If you are, then if you have questions for Doug, please send them to him, and I'm sure he'll be happy to answer you. Myself, I came away learning that languages, I'm a bike enthusiast, are kind of like bikes. You have different categories. So you have racing bikes, endurance bikes, hybrid bikes, urban bikes, and fun bikes. So that's what I took away. I never knew that. So thank you very much. You enlightened me a lot.
Yep.
And enjoy the rest of your day.
Thanks very much.